should be up and running now. Okay.
Okay.
Okay. Yeah, my Wi-Fi is a bit slow today, so I'm already sorry in case my audio breaks up. Okay. Yes, so I'd like to start and introduce a project of mine, which is basically a design pattern for analysis automation on interchangeable distributed resources using Luigi Analysis Workflows, or short, LAW. Okay, so but before I start with law itself, I'd like a little bit to talk about my background, because this is basically the reasoning for why I'm doing this project. So I'm coming from the physics analysis search side. So I was doing a search for TTH, where the Higgs boson decays into a BB bar pair. And this analysis is quite large and quite complex. There were about 500,000 different tasks to process in the entire course of the analysis. The processing took place on the grid on a few HT Condor batch systems. So at my home university back then and at CERN, several GPU clusters for training, and also on local machines. And the user storage we required was about 100 terabytes. So I'm not talking about central data, but just the data after that. So after, in our case, mini AOD in CMS terms. And this data needed to be stored across several sites on local storage, but also on DropBox, CERNbox, so via different protocols. The data flow was quite complex due to sophisticated techniques that we used at that time as a large in a large group. So we basically had a mixture of BDTs, DNNs, which needed to be trained. So you can imagine there's a data flow where data is merged, and then maybe a model is applied again on other data. And yeah, we included also matrix element methods, which are quite intensive, of course. And another driver of the entire flow was the number of systematics, of which we had about 80 systematic variations. And for many of these variations, the entire analysis, or at least parts of the analysis, needed to be just redone. And another constraint is, of course, I mean, doing a TTH analysis, this implies quite that you can also maybe do a TT bar analysis. And we shared this with a different analysis. And so all the parts must be, at that point, must be operable by everyone at any given time. So this was basically driving the complexity of the analysis. Before going forward, I like to make one step backward and look at the landscape of HEP analysis. And here I like to introduce two main and very simple metrics to describe an analysis, which is the scale, which I would describe as the measure of the resource consumption and the amount of data to be processed. And then there's the complexity, which is kind of the measure of granularity and inhomogeneity of the workloads that is involved in the analysis. And here on this little graph, you can see when the scale is low and the complexity is low, then a single machine would suffice, and single commands just executed on the command line would also be okay. When you increase the complexity, you already need to have good scripts and good code structure. When you have a large scale, but not that large complexity, you would likely work on, for example, the grid or on several batch systems. And when both of these, when the analysis is both complex and large scale, I think at this point a dedicated analysis workflow management is very necessary. And today's and definitely future analysis tend to be both large and complex. And this entails that the requirements between many workloads are undocumented, as they mostly only exist in the physicist's head. And this is a big drawback, of course. Then there's the problem of manual execution, manual steering of jobs. There's bookkeeping of data, different versions of data, revisions of code, and so on. And this entire thing is error-prone and time-consuming. And I think everyone who did also a search or a physics analysis knows what I'm talking about here. This can be very, very messy. Okay, going on, this is an example of how this is just a part of analysis, but this is visualized. And every of this, I'm not sure if you can see this, I will zoom in now. Every circle is basically one task, And every line between two circles, so each edge corresponds to data which is flowing from one task from one workload to another workload. And all of this has to be either scripted somehow into the code, or it's mostly living, yeah, as I said, in the head of the physicists. So then, before introducing law, I'd like to finish here this introduction part with some motivational questions, 3 of them. So the first one is basically the question if an analysis depends on where it runs and maybe even where it stores the data. And I would say that these decisions, so where it runs and where data is stored, should actually not dictate the code design, but oftentimes this is just the case. Then in a group, in a larger group, when a postdoc, a PhD student, master student leaves, here the question is, can someone else run the analysis, or is information lost, or is maybe a new quote-unquote framework required? So this is the worst case, of course. And this might sometimes be the case because, yeah, the workflow is often not documented. And with workflow here, I mean the glue basically between the workloads, as it is existing in just, yeah, as soft information. This is often just not checked into any repository. And the last part is targeting preservation. And here the question is, when an analysis is published, are people actually investing time to preserve their work? And can it be repeated after, let's say, a few weeks, few months, or a few years? And we want this answer to be yes, but we all know that it's maybe not that easy. And here a solution would be if the daily working environment, or yeah, analysis workflow management system should or could provide preservation features out of the box. Of course, not full preservation, because this is completely complicated, as most of you know, but at least some preservation features should be provided out of the box. Okay. With this in mind, so having this scale and complexity introduced, to shortly introduce Luigi, which is a nice way to tackle the complexity. Luigi is a Python package for building very complex pipelines. The development started in 2012 at Spotify, but now it's completely open source and driven by the community. What I find very attractive about it is that it's very simple and it has very, very simple building blocks. So first of all, a workload. Before I was always talking about workloads. In Luigi, those workloads are defined as so-called tasks or task classes. The dependency between the workloads or the tasks has the form that tasks can require other tasks, and to output stateful information, tasks can produce or output targets. And this is most often, these are files. And a target is just something which has in the core API basically is just something which has an exist method. When the target exists, that's fine. When it doesn't exist, it has to be produced. And then Luigi has parameters to customize behavior. We will come to this shortly. And the benefits of this very simple structure is, of course, that Luigi only, of course, then processes what is really necessary, and that error handling and automatic rescheduling of these tasks can be adopted. So for example, on the right-hand side, we see the an interface that comes with Luigi, which is basically a very small web server. And here one can just visualize what is currently running, what needs to be run, what did run in the past. And from here, you can, for example, also just reschedule tasks. Okay, Luigi in a nutshell. So this cell basically contains 80% of what you need to know about Luigi. We can quickly go through it. It's really not that much. So first, import Luigi. I think this is clear. Then, as I said, each block or each workload is defined as a task. And here, in this case, as a task class. And here, let's define an inference class. This is an example for a parameter. In this case, a data split parameter. Here, it's a choice. You have the choice to choose between test, valid, and the train data set, the train split. And to run this, or when you run this, these parameters that are defined here, these class members, they are translated into command line arguments, basically. Then, as I said, a task can require other tasks. And here, the inputs would naturally, for example, require that the evaluation did run before. And here you would define it as this. You import the required task, and then you pass along or pass upstream the parameters. So of course, when you run the inference for a certain split, you would also require the evaluation for that split. And this is what's done here. Then the output, as I said, the output of a task is a target. And in this example, I just define a local target, which is a local file. And it makes, of course, completely sense to encode all the significant parameters into the output path, which is done here. And then there's a run block, of course, which takes basically the inputs and should produce whatever the output is. This is very, very generic. And here you can break out, do a popen and call something in C++ if you want. But here is the connection is happening. So output here is, of course, what we define above. Input is, naturally speaking, the output of the requirements, right? So input would be the output defined by this MVA evaluation task. And then with these objects or with these paths, basically you can do whatever you want. In this case, very, very generic placeholder for doing whatever an inference does. So this is basically Luigi on one slide. Then when you want to run this inference task here, this would be done in pure Luigi. This would be done like this. You call Luigi from the command line. You tell it the module that you want to run, or the module where your code is. You give it the name. The name of the task to run, and then here you put your parameters. We define the split parameter, so you can just put the split parameter here, give it a value test, and so on, and you can pass along other parameters here. And what Luigi does is, let's call this inference task the triggered task. On the right hand side, it's here, and Luigi builds up basically a dependency tree. So when this guy here is the triggered task, it would go up this requirement tree and build up this graph structure here. And a task is considered complete, just like in make, when all its targets exist. And then when this tree is built, then it's just run with, for example, a configurable number of workers, and of course on your machine. And this is very make-like and very simple. And this way, of course, this way Luigi just executes what's really necessary to execute. This is an example of what a bachelor student produced after 2 weeks. Here it's quite small. Feel free to zoom in. This looks very complex, but actually this is a very, very standard use case. And to have it visualized is a very nice thing. It's a very nice thing for the bachelor student to have, because he knows or she knows what he's actually doing there. And I mean, as a supervisor, you can also see what the person is actually doing there. So this is very nice. This interface is very, very nice to have. To have this web browser running is of course optional, but it's a very nice addition to the Luigi tasks. Okay, now let's go to law. And with law, I mean Luigi Analysis Workflow package. So while Luigi is a perfect tool to model the complexity of workflows, and with its very simple structure, and it's very easy to extend, law itself extends Luigi. So it does not replace it, it's just an extension on top of it. And the main goal of law is to decouple the algorithm code. Here it's visualized on the right-hand side, to completely decouple the actual payload or the algorithm to run from where it runs, so the run locations, from where it stores data, which are called storage locations, but also from software environments. And the aim is, of course, the aim of law is, of course, to provide a toolbox to follow a pattern, a design pattern for analysis. There's no constraint on the data format. There's no constraint on the language that you call from within the run block. There's no fixation on any resources. There's really no constraint. And by this means, I would say that it also doesn't qualify as a framework. It's really just a toolbox to follow a design pattern. Okay, so let's go into a very quick example here in the notebook. Before we start, let's load the IPython magics that we need downstream. just quickly run this cell here. This, okay, I think. Okay, this is somehow slow now. I will just go over it. Damn it. Okay, let's wait a second. But yeah, there are IPython magics in Low in these contribution packages. And basically what we need is this ilaw, which is running tasks in the current session. Maybe in the background, I will just restart another notebook. It's a bit of a pity. And go on here. So the example task here is just to write a task that takes an input parameter and multiplies it by 2 and then saves the output into a file. So simple as that. This we would do this by defining this times 2 class here, which is a task, of course. We define the parameter as n and define the output as being just a local file target. This time it's a law local file target and not a Luigi local target anymore. And the local file target in law has way more convenience functions, as we would see a little bit later. Then in the run method, so I have now 2 implementations for this. One is the very verbose way, the very manual way that I think everyone knows by in the end just using plain JSON to dump the data. What we do here is we get the output, we ensure that the parent directory, in this case it's data, exists by calling output parent touch. Parent is the containing directory. By calling touch, we ensure that it's there. Then here we define the output, which in this case we want to store the input value, but also the output value, so the input value times 2. And then we store the data in a very Pythonic way. So I hope that the notebook is connected now again. Okay, it's not. Okay, I hope this is the last time that I have to restart the notebook. Just 1 second. Yes, so we can proceed. Let's load that task. And then when this task is defined, we can just run it on the command line. This would just be law run, and then the task and the parameters. Here in the notebook, it's ilaw, so interactive run and this task. And here we run it with the parameter 5. When we do that, we see a bunch of output, but the most important thing is that so is running this task. It's of course immediately done, and then there's a nice small summary. If we wanted to run this task again, we see that the output is different because it actually didn't do anything, and this is also what it's telling. It did not run any tasks. Of course, the output was already existing. We can inspect the results by adding, for example, the print status method and then a recursion level. Let's just execute it. So if here we see in the output, we see the task, we see the outputs of the tasks or the targets and the current status. In this case, it's of course existing, and we can also check out the content. And this is exactly what we've just written into the file. This recursion depth is, for example, when times 2 would have requirements, then we could also print the status of the requirements by increasing the level. So this is basically the depth in the tree that I showed before. We can also remove the output again if we want to do that. Let's do this here in this quick example. Here, this is even in the interactive mode, asking what to do. Let's first do the dry mode, and then it tells you what it would remove. We can also add the mode right behind it. So here it's running the dry mode, and we can just remove everything. If we wanted to print the status again, now it's absent, and so on. But I think this is pretty clear. We can now, of course, rerun this task, and we will see this in the status that it's there. So this is basically the way of starting tasks and inspecting the results. So moving on. This is the same task now, a lot shorter because of what's happening here in the run block. Now I'm using so-called target formatters, which is a feature of these local file targets. Here I can just pass, so create this instance here of the local file target, call this dump method, pass data, and tell this dump method which formatter to use. In this case, it's Python, of course, and then all the arguments passed here are forwarded to the actual dump implementation. And in Law, there's a variety of formatters, from TensorFlow over Keras, even Cofia formatters, just to really accelerate working with these objects. And yeah, this works just the same way. Okay, now to the three main goals of Luigi. So first of all, is the abstract storage, and this is done by having remote targets. And here the idea is to work with remote files and directories completely as if they were local. And the remote target implementation that I created is based on the gfile to Python bindings. So there's support for all the WLTG protocols from dcache, xroot, gridftp, GSIFTP, SIM, and so on, plus DropBox is already included. And the API, the underlying target API, is completely identical to local targets, so there's no difference at all. Under the hood, there's features like automatic retries, round robins, for example, round robin access over different doors if this is configured, local caching, and many more features. This is an example of how to use those remote targets. So here in the example, I put the DropBox targets in a configuration file. You would put basically your credentials, your DropBox credentials, just like that. And then on the right-hand side, you can see how to basically deal with these targets. And all the methods on the right-hand side, they're, as I said, completely identical to the local targets. So when changing, for example, the class of a target and not the code below it, everything should just run the same. And here, I played around a bit with the targets. One can define a directory, define a target in it, so a file basically in it, and then dump some data into it using the NumPy formatter, list the directory again, load the file again, or load the data basically again. So my file would be a target. Using load with the formatter NumPy would directly load the file, maybe in a local cache, maybe not, depending on how this is configured, and then just directly give you the data contained in this file. And there are some other, of course, API calls to play around with. And here I linked an example that you can run locally in, for example, in a DropBox, in a Docker container to check out this DropBox targets. Next slide, the abstract job interface, and this is done by having remote workflows. And here the idea is to have submission to batch systems built right into the tasks, so you wouldn't see it, the actual submission, and there's also no need to write extra code. And currently supported job systems are hdconda, LSF, glite, arc, and there's an open pull request for Slurm, which I didn't have time for during the last weeks of lockdown, but this is hopefully coming soon. Mandatory features here are, of course, automatic resubmission of jobs, full job control. So when you submit anything or when you run a task, you can control, for example, the number of tasks per job, the number of parallel jobs that are submitted in parallel to a job system, number of job retries, early stopping, and so on. And there's also a dashboard interface. And here is a small example.
Just so
taken
you know,
from.
you got about 5 minutes, including questions.
Okay, yeah, I will speed up a bit. So then, for the sake of being fast here, let's look on the right-hand side. There is a task. Here it's a workflow. If you're interested in what is the workflow, check out this slide again later. But it's basically a simple way to have, let's say, a batch of tasks written within just one task. And in this example, here, this would split up into 26 different tasks, and each task would just convert a number into a character and write it into a file. So it's very simple. And this has immediate capabilities to run on htcondo by just inheriting from this htcondo class here, htcondo workflow class. And this is it, and there's nothing else needed to run it. And if you're interested in that, the next slide, okay, this would be the output if you would run it. So it would submit the jobs and then go into a polling for the job status, and then continue with maybe local tasks. Yeah, so this is basically the idea. And there's a executable example if you click on this link, but for that you would need permissions to run Analytics Plus. Okay, last item is the abstraction of the software environment, and this is done by sandboxes. So yeah, I mean, as I said before, in many analysis, there are diverging software requirements between different workloads, and this is a great feature, but this can also be a challenge and even a problem. And in law, there's a mechanism called sandboxing, and the idea here is to run an entire task in completely different environments. So on the right-hand side, you can see a graph, and for example, here, this inference task, the one at the top, this could run in a Docker image A, the next task would run in a Docker image B, then something is running in a subshell, and so on. And currently implemented are subshells, Docker images, and Singularity images. This in here is an example of how sandboxing is configured. It's actually just, yeah, 2 lines. This is a task which not only inherits from the base task, but also from a task called sandbox task. And this allows you to define a sandbox identifier basically here. For Bash, this is just referencing the subshell in its file to load. For Docker containers, that would be the Docker image name, and for Singularity containers, it would be the Singularity container name. And everything else just remains the same. So this run block here would be encapsulated in this environment. And when running this here, this would take from the environment a variable called my_variable, which is not existing in the actual environment, but it's existing in this test environment here. And when you execute this task, this would be the actual output when running from the command line. I didn't have the time to implement sandboxing within notebooks, but most of the time you would actually run this from the command line, and this would be the output. So you will see that everything is starting normally, and then at some point here, and the output is here, that a sandbox is entered, then this run method is called in the sandbox, and then the sandbox is left again. And this works exactly the same for Docker images and Singularity images. Okay, this brings me to my summary. So yeah, many HEP analyses already or are very likely to increase in scale and complexity, and a resource agnostic workflow management and automation is actually very essential. And I think what the community needs is a toolbox that allows you to follow a design pattern and not another framework. And Luigi here is able to model the complexity of workflows while Law provides the convenience and also the scalability in the HEP context. And the achievements are, of course, that all information is now completely and transparently encoded in task, target, and the dependencies between them. Everything becomes basically executable with one command. And yeah, this allows for full automation of end-to-end analysis. Thank you very much.
All right, thank you very much. So we have, I'll give a couple of minutes for questions. Here's a couple of questions. So right now, looking at the top questions, and of course, the ones that we won't be able to comment on will go on Slack, and hopefully you'll be able to respond. So does an analysis have a single central instance of Luigi, or do all analysts have their own copies? And if so, do you share intermediate data between the instances?
I think the question that targets instances is, I think, kind of referring to this web interface. Sure, I mean, many analyses can share the same web interface, but you can actually also spawn your own interface if you want to run uninterrupted.
Well, let me rephrase maybe. Like if 2 people are working on an analysis, do they have to share control over a single workflow, or do they, you know, if one of them is going off and trying something, do they get their second copy? And if so, do they share, do they share intermediate data, or do they have to reprocess the whole chain?
I mean, they can, but they don't have to. If they define their targets to be accessible by both of them, I mean, yeah, sure, they can share the data. If they want to store the data somewhere else so that the other person is not interrupted by that, and yeah, he or she can, of course, save the data somewhere else. This is completely flexible.
Okay. So next question, what are your thoughts on Luigi versus SnakeMake versus Nextflow?
Yeah, and then there's Airflow and all the other tools. Yeah, when I started, Luigi was one of the most prominent ones, and I started, I think, 5 years ago with this project as a side project. Some of them are lightweight, and I think such a tool must be lightweight. And I think there are also some workflow tools which require you to run a database in the background, and I personally don't like that. I like it when it's really just Python code and doesn't require any server to run if you don't need to. And I found some of these frameworks to be, yeah, they have different advantages and disadvantages. And for my purpose and for the purpose of having this easy scalability on HEP infrastructure, I liked the idea of Luigi the most.
Okay, thank you. I guess one more, which I think maybe adapts slightly, because I think you addressed some of it. So you outlined a number of ways to interface to batch systems, for example, and this would seem to overlap significantly with what Ganga does, for example. So it's kind of in the same space. Is there? Do you see them filling different niches, or is it possible that one could exploit the other?
I didn't hear the first sentence. Can you repeat maybe?
Sorry. So this was with relationship with Ganga, which we had a talk yesterday.
I couldn't really follow the workshop yesterday, but from the context, I understand that it's basically a tool to access many batch systems. Is this correct?
Yeah, I suggest maybe we take that one offline and we have a question on Slack. So yeah, and so unfortunately for time, we're going to have to cut the questions there. But again, the questions will go on Slack, and hopefully we can have a good discussion there. So, so yeah. Thank you again very much, Marcel, for the very interesting talk.
Thank you.